This lesson is on section 6.2, inverse functions and relations. If you were able to print the guided notes worksheet, this presentation will go with that worksheet that you printed. So to graph the inverse relation, okay, in front of you right now, we have this relation, right? It's also a function. I know it's a function because it passes the vertical line test. So these points were plotted. I'm just going to highlight them here in blue. So 0, 2 from the table of values, 1, 5, 5, 6, and 8, 9. Right, so this is a relation. It's also a function. We're going to graph the inverse relation. So what we do, you can reflect each point across the line y equals x. If I graph the line y equals x, it has a y-intercept of 0, and it has a slope of 1. So up 1, right 1, up 1, right 1, up 1, right 1, up 1, right 1. Right, so these red dots, this is the line y equals x. We're going to reflect each point over this line. So for people who are visual, we're going to take the point 0, 2 and reflect it over that red line. That becomes 2, 0. Right? The point that was at 1, 5, that becomes 5, 1. And do you see how if you folded this like piece of paper, right? Imagine this was a piece of paper and we could fold it at the red line. Do you see how it would touch from blue dot to pink dot? That's what we're doing here. Now it's kind of difficult to exactly get the ordered pairs just visually reflecting it. So the other trick is to switch the x and y coordinates, right? When you reflect over the line y equals x, it's going to switch your ordered pairs. So you'll have 2, 0, 5, 1, 6, 5, and 9, 8. So I'm just going to plot those points so you can see the reflection. And then we're going to connect the dots so that they mirror the original relation. So the original thing we can call, let's just call it f of x, just to identify it and give it a name. So this blue one is f of x. To label the inverse, which is the pink one, the notation is this. It's an f with a -1 power of x. Now, it's not an exponent the way you're thinking of exponents, like x squared. That's just the notation. It's a -1. It means inverse. Make sure it's in that location. Don't write it like this, right? That is not correct notation. So make sure the -1 is exactly in that location. So this is our inverse f of x. That's how you would say that, inverse f of x. Now let's talk about the domains and ranges of each one. For the domain of the blue one, the f of x function, our smallest x value is 0. Our largest x value is 8. And everything in between that is used. So we use everything from 0 all the way to 8, and we would write our answer like that. Our range for the f of x function, our y values, starts at the lowest value y of 2, and it goes all the way up to a y value of 9, from lowest point to highest point and everything in between. Now let's talk about the domain and range of the inverse function. The inverse function has a domain with a smallest x value of 2, right here, all the way to an x value of 9. The range of the inverse function has a lowest y value of 0, going all the way up to that pink dot at 8. Do you notice that the domain and ranges flip-flopped? This domain became this range, which hopefully makes sense because we switched all the x's and y's when we went from the original relation to the inverse relation. So the domains and ranges will just flip-flop. Just make sure you pay attention that you use x and y appropriately when you do this. All right, so here we have f of x. We have a function here, f of x, and you're provided with a table of values. So pause the video and go ahead and plot all these numbers. So this is a parabola. It is a function. How do I know it's a function? So pause and answer in your head. It is a function because it passes the vertical line test. You can also say it's a function because for every input there is one and only one output. For every x there is only one y, right? I like to look at the vertical line test, right? It passes that vertical line test there. Now, the next question is, let's graph the inverse, right? Let's graph the inverse function. Let's graph the inverse. Is it a function? So in order to graph the inverse, we're going to reflect it over the line y equals x, just giving us this visual here. And I'm going to plot those points. Again, you can go ahead and just reverse your x and y column. Go ahead, pause the video and plot all those points and see if you can answer, is it a function? So here is the inverse. I'm going to label it. Inverse f of x. It is not a function. The inverse is not a function. How do I know that? Because it fails the vertical line test, right? If I draw vertical lines, it hits in more than one spot. Now, there is something that we can use as a shortcut to deciding if the inverse will be a function or not graphically. Because I switched x and y, right? All the x's became y's. So on the original pink function, I can draw horizontal lines, and that will tell me if the inverse will be a function, because those horizontal lines, when they get reflected over the line y equals x, they would actually become vertical lines for a vertical line test. So I can test the horizontal line test on the original function to decide if the inverse will be a function. So if the original relation, okay, that's the pink one, if the original relation fails the horizontal line test, then the inverse will not be a function. Let me give you a bunch of examples here. I'm going to come back to that in a second. So this first picture, is it a function? Yes, it is. It passes the vertical line test. Would the inverse be a function? Would the inverse be a function? So without graphing the inverse, what I can do is I can do a horizontal line test, HLT, horizontal line test. If it fails the horizontal line test, which is this one does, it fails, the inverse is not a function. So this would be no, the inverse is not a function. Let's try another one. Let's look at this graph. Is this a function? Yes, it is. It passes the vertical line test. Is the inverse a function? Well, let's do the horizontal line test on this. Yes, the inverse would be a function because this passes the horizontal line test. Is this a function? Yes, it passes the vertical line test. Would the inverse be a function? Yes. This passes the horizontal line test. Oops, sorry. Is this a function? Yes, it passes the vertical line test. Is the inverse a function? No, because the original relation fails the horizontal line test. Is this a function? Yes. Is the inverse a function? No. It fails the horizontal line test. Okay? Now, if something is a yes, yes, we call it a special name, a one-to-one function. A one-to-one function is if both the relation, which is the original thing that we're looking at, if the relation and the inverse are both functions, then it's a 1-to-1. So look at these and pause the video. See if you can point with your finger which one of these are 1-to-1 functions. Which of them had yes, yes? So which one of these are 1-to-1 functions? Yes, yes. This one, this one, that's it. Those are the 1-to-1 functions. Okay, so now what we would like to do, let's go back to this example we were looking at here. We've graphed the original relation in pink. It was a function. We graphed the inverse. The inverse was not a function. What I'd like to do now is write the equation of that green function. Write the equation of it. So what is that equation? What does that look like? Inverse f of x equals question mark, right? Here's how we're going to do that. To write the equation of the inverse, you're going to follow these steps. We are going to switch the x and y values. So remember that f of x is really a gigantic y in disguise, right? It's y equals. So we are going to literally switch the x and the y in the equation. Okay, we are literally switching the x and the y that are in the equation. Step 2, we're going to solve for y. We're going to try to get the y by itself. So for this problem to do that, you're first going to get rid of this power of 2. So we're going to square both sides. Sorry, square root both sides. So we're going to do square root, square root. When you do square root, what shows up? Plus or minus. That square and the square root on the right-hand side cancel each other out. Again, we're getting the y by itself, so we're going to subtract 2 from both sides. I'm going to write this with the -2 first. That's just the most normal way to write this in the math world. And then I'm going to multiply both sides by 2. So this becomes y equals -4 plus or minus 2 square root of x, right? I'm distributing that power of 2 over there, right? And then last step is just make sure you're labeling it as an inverse. So inverse f of x equals instead of y equals. And that's your inverse equation. You might see some textbooks do inverse of y like that, and they use y to the -1. That's perfectly fine. Now, let's talk about domain and range. Remember when we did this graph back here that the domain and ranges flip-flopped. So what you need to do is look at the original relation and look at your inverse relation and at least figure out some of this so that you can flip-flop, right? The domain and range of either of these. Depending on your knowledge, that will depend on what you fill in and which one you actually do. So for me, I know, and for you, we know that the original relation up here was a quadratic, right? It had x squared in the problem. And I know the domain of a quadratic is all real numbers. So that's going to make my range down here all real numbers. Now the next thing you can do is figure out the range of the quadratic at the beginning of the question here, or you can find the domain of the inverse. I think it's easier to find the domain of the inverse, and this is an introduction to radical equations. When I look at this radical equation, when you have a radical, a square root of x, what cannot x be? What can't x be? X can't be a negative number, right? X can be 0, square root of 0 is 0. X can be 1, square root of 1 is 1. X can be a decimal, that is totally fine. But X cannot be a negative number because the square root of a negative number becomes an imaginary number, and we're not dealing with imaginary numbers here. So I want the X value to be 0 or greater. I don't want to go below 0. So my domain for this question is X is greater than or equal to 0, which means the range for up here was, Y is greater than or equal to 0 up here, because the range is Y values. If you knew the range of that quadratic, great. You could have done that first and then used it for the domain. So it's a little bit of a puzzle. You got to use the knowledge you have and what you think is easiest to try to figure out the domains and ranges. But the key thing is that they flip-flop. So as long as you can figure out some of it, you should be able to figure out all of it. So now let's do another example. Find the inverse equation of this f of x function. We know this is a line, y equals 2x plus 4. Let's literally switch the x and y. Go ahead and pause the video and try the rest on your own. So I'm going to subtract 4 from both sides, and then I'm going to divide by 2. Oops. Now this is a linear function. So I'm going to write it as, sorry guys, I'm going to write it as a linear, the way we write lines, y equals mx plus b. So I'm going to go ahead and do sharing is caring. There's my y equals mx plus b. And then I'm going to change this to inverse f of x. And there's my equation. Let's go ahead and state the domains and ranges of these. They're both lines, right? This has a positive 1/2 slope. This has a positive 2 slope. Hopefully, we can easily fill in the domain and range of each of these is all real numbers. The last piece of this section is verifying that this is actually the inverse. There's an algebraic way to verify that this yellow highlighted inverse equation is actually the correct answer. So to verify that two functions are inverses, we use composition functions, which is the f of g of x, which we learned the other day. So in blue, if f of g of x equals x, and vice versa, if g of f of x also equals x, then those two functions are inverses of each other. So let's do it with this example that you have here. So I am going to check. I'm going to call this thing, we'll call this thing f of x like it is, and we'll call this thing down here g of x, just to match this notation. So we're first going to find f of g of x. So I am going to replace the g of x function with what I got for this g of x function down here, 1/2 x minus 2. That's my inverse. I'm going to take that inverse equation, 1/2 x minus 2, and substitute it into the f function everywhere I see an x. So 2x plus 4, I'm going to replace the x with the inverse. So now I'm going to distribute, combine like terms, and we get x. That's what we were trying to get. We wanted to get x. And then you have to also check it the other direction. So I need to check g of f of x. So I'm going to start with the f of x function on the inside and put that 2x plus 4 into the g function, in this case, the inverse function. So 1/2 x minus 2, I'm going to replace the x with 2x plus 4. I'm now going to distribute, simplify, and you get x. You have to get two happy faces. You have to get two x's. X the first time and x the second time. It has to work both ways. So if the first time gets you x, but the second time doesn't, they are not inverses of each other. You have to check both of them. One's not good enough. You have to show all your work because we're considering this pretty much like a prove, right? We're verifying it. And if one of them doesn't equal x, just stop, right? Don't even go through with the other one. So as soon as one of them does not equal x, that's it. And it always has to be x, not negative x, not 1 over x, not 2x, not x squared, x. It's always x. So if you feel confident, pause the video and go ahead and try these 2 examples. If not, I'm going to do the first one with you here. So we're going to determine yes or no, are these inverses of each other? And the way we're going to do that is we're going to do f of g of x and vice versa. So I'm going to take g of x, put it in here, right? All I did was replace it. And then I'm going to take this 1/3 x plus 1 and put it into the f function everywhere I see an x. Distribute. Combine like terms. And this is a no-go. No good. So these are not inverses, right? F of x and g of x are not inverses of each other. Notice I'm not even going to go through and do g of f of x because there's no point. But it was also a no. It did not come out to be x. On example number 2, same thing. We're going to do h of j of x and vice versa. They're telling you up here for x not equal to 1 or 0. That's just they're telling you the domain. They're saying that don't worry about when x is 1, because if you make x equal 1 here, right, you get a divide by 0 error, and that's no good. Same thing down here. If you make this x value as 0, you've got a divide by 0 error. So they're saying don't worry about these domain errors. We're telling you x cannot equal 1 and x cannot equal 0. That's the only reason that's there. So h of j of x, we're going to replace j of x with this guy. Right? So I just replaced that with that. And now I'm going to take the 1 over x plus 1 and put it into the h function everywhere I see an x. Now you are going to show every little step, right? Because you're proving that this is actually equal x. So you have to show your arithmetic, show your algebra. So I'm going to do a keep, change, flip. And so that gets you x. Now I'll do j of h of x. So h of x, I'm going to replace it here. That just became that. And then I'm going to take the 1 over x minus 1 and put it into the j function everywhere I see that. So 1 over, and the plus 1 is off to the side. So keep, change, flip. Bring down my plus 1. Notice I'm showing every itty bitty step because this is like an algebraic proof here. So I got 2 happy faces, 2 x's. So yes, these are inverses. And that's your lesson. Hope you found this helpful. If you have any questions, let me know.